So, to summarize, we have earlier looked at the various physical design automation steps like partitioning, placement, floor planning, routing and so on. Later on, we looked at some of the performance driven issues. We looked at performance driven placement and routing, and also some techniques for physical synthesis, how you can make some timing corrections. So, now let us try to look at the overall picture now for this kind of high performance designs where this performance driven issues are important. So, what should be our so called performance driven design flow? So, we look at into the overall picture in this lecture. Okay. So, let us have a quick look at the so called performance driven physical design flow, which is more or less a standard practice in modern day VLSI circuits. Okay. So, here what we are trying to tell you is that whatever techniques we have looked at, let us try to combine it in a consistent design flow. Now, here we shall see that there are a few things like static timing analysis which we do not consider as a step. We consider this as a tool, and this tool can be used a number of times in different phases of the process. Okay. Similarly, buffering is a very common technique which may have to be done multiple number of times. There can be an initial level of buffering, maybe after one cycle you find that still some timings are not being satisfied, you may have to do some more buffering. So, there are some iterative steps which need to be carried out. There are a lot of iterative steps, and even at the end you may find that still a few things are not being met, you may have to do a few more corrections there. Okay. So, let us revisit the typical physical design flow once more. Now, the typical physical design flow starts with something called chip planning. Well, we did not use this term earlier, we called it floor planning placement, but in chip planning we include three different things. Let me just try to just highlight. So, in chip planning we are talking about something called chip planning, which is also a very commonly used phrase. First is a step called IO placement. So, IO placement means for this chip where to place the IO pins or which pin should be carrying which signal. This is the IO placement, okay, like this. Then we can have floor planning. Of course, I said that most of the circuits today are based on standard cells. Floor planning and placement are identical in those cases. So, in floor planning we are telling which standard cell has to be placed in which rows, and there is another thing which is done together, power planning. Because now that we have the standard cells already laid out, we know that where are the power connections that we need, VDD and ground here, VDD and ground here, like that. So, you also plan overall whichever technique you will be using to supply the power supply and ground lines, whatever way you do. Okay. So, this kind of a power planning network also you do. So, this the entire process is sometimes referred to as chip planning, that overall the chip, how does it look like, where are the pins, what will these pins carry, these are the cells, which cells will be put on which rows, and how will the power network look like, that will be powering, that will be providing power to the different rows and the cells. Okay. Okay, fine. So, here there is a something called trial synthesis, which is the initial thing which you have got. This provides the floor planning tool with an estimate of the total area that is needed. You can see that, and in this estimate you should provision for buffers, so additional space for routing and gate sizing. Some gates may have to be made larger, so you have to keep some additional spaces for these things, right. So these earlier we did not talk about all these things, but now we are saying that we need to keep provisions for all these things which need to be added in later stages of the design flow. Then logic synthesis and technology map, well, of course this can be done earlier also. It produces a gate level, cell level netlist. Well, when you are doing a floor planning, sometimes these are done together, or this can also be done earlier. Okay. So after you have placed the cells, you can carry out global placements. Now global placement, whatever I have said, that you place the blocks or the cells in rows of the standard cell. Now again I have said that in a typical VLSI design flow you cannot do the thing in one go, it is a repetitive step. So you make a placement, you may find that something is not working properly, there is a lot of congestion somewhere, there is a lot of delay in some places, you may have to change the placement continuously. Okay. So here what I am saying is that the process of global placement, it typically assigns locations to the objects where means I shall be showing a slide. So here we look at the clustering information. You try to spread the cells uniformly across the chips. Like what I am saying is that you may find that initially your chip plan looks like this, where this dark region means there is lot of clustering and congestion here. Many of the cells, the global placement tool says that they will be mapped here. So as you proceed, this region slowly spreads, it spreads across the whole chip, and maybe finally you will be getting something like this. So your whole placement must be spread across the entire area of the chip. Okay, something like this, very roughly I am saying. Then after the global placement is done, you see you cannot synthesize the clock network before you know where your flip flops are located. So once you have done global placement, you know where your registers are, where your flip flops are, the sequential elements. So with that information you can proceed to synthesize the clock network. So this clock network, as you know, we have seen earlier, this can be either a simple clock tree, say like an H tree or an MMM or something like that, or you can have a more flexible network consisting of a tree at the higher level and a very regular mesh at the lower level. Normally for processors we have this kind of hybrid, because in a processor chip there are a lot of points where you need to carry the clock signals. There are a large number of target or sync points for the clock signal. So you normally have a mesh in the lower level and a regular tree at the upper level, maybe an H tree usually. Okay, fine. So this is just a sample slide showing a buffered clock tree in a small processor design, where these rectangles indicate the places where buffers have been inserted, okay, and the lines indicate the connections, and the X indicates the points where the clock has been taken. Fine. So after placement is done, so the locations of these cells are, well, they're aligned to a grid, and after this you see, during placement normally we do not have the grid concept. You can place a cell virtually anywhere, but when you do routing you often have some rows and column concept, tracks and some columns. So there you have to align everything to a grid. So after this initial level of placement is over, you have to do an means alignment of these blocks or cells to grid locations, to a uniform grid. And after you have done this, so you can proceed for global routing and layer assignment, where layer assignment says for each of the routes which layer, these layers are typically metal layer, which metal layer will be used to connect these nets. Now, global router typically completes the routing on a single net, like you say the Lee's algorithm. They will, the Lee's algorithm or the Hadlock's algorithm, they will try to find out a route on a single layer, single metal layer. Okay. Now, here when you do routing, you may also land up in something called wiring congestions. You may find that in the chip there are many areas where the wiring congestion is pretty bad. So, you may have to do an iteration here again. So, you do something called congestion driven detail placement. Now, you again modify your placement based on this information. Like I am just showing an example. This shows you over the area of the chip, these peaks indicate the levels of congestion. There is an area where lot of congestion is there. Now, with iteration, you try to reduce congestions, and you will see finally there is almost no congestion. Okay, they are uniformly placed. Congestion means, I refer to congestion with respect to routing. So, if there is a congestion, it is quite likely that during the process of routing you will find that you are not able to complete the routing at all. Okay. So, such a scenario should not occur. So, you should do something which I just mentioned called congestion aware detailed placement. So, you modify the placement again such that the congestion values get improved to a significant extent. Okay. So, now after that you proceed to detailed route. Now, the global routing gives you approximate routes. Now, detailed routing will just assign the exact horizontal and vertical metal layers for these routes. Now, there is an additional optional step like these routes which are generated, the wires. So, you may have to go through another iteration which consists of reliability, manufacturability and electrical verification. Like let me tell you, reliability refers to, means you have seen the process of channel routing. There are horizontal tracks, vertical tracks, and there are some via connections that connect the points across layers. So, you can have 2 layers for multi-layer channel routing. Now, the via connection provides with, you can say, some source of unreliability, you can say, because you are ultimately drilling a hole and making a connection across 2 layers. So, higher the number of via connection, higher will be the possibility that there is that your chip can fail because of some misconnection, loose connection or something like that, wrong connection. So, one objective may be to reduce the number of bends in the connection which may indicate number of via connection. So, many a time means on the same layer when routing is carried out, instead of using sharp bends, you use something like a 45-degree bend, because sharp bends are places where the metal is likely to break and form a disconnection, right. These are something which are called reliability and manufacturability. These are something which have to be looked at it after everything is done. And electrical verification means, well, after you have laid out the wires, you see the length of the wires, whether this separation is sufficient, width of the wires are sufficient. There are some very simple set of design rules, you can say. So, all those design rules are verified by a design rule checker, which can tell you that, well, here are the places where I find some violations, you please correct these things. So, in that case you may have to go back and make some corrections there, some rules are getting violated. Okay. So, after everything is done, you proceed for mask generation, where So, every circuit element and interconnection are represented by rectangles. Rectangles are on various layers: polysilicon, diffusion, metal, metal 1, metal 2, metal 3 and so on. Fine. So, let us look at the overall flow in the form of flow chart. So, in the first step, we assume that already chip planning is done. Chip planning is given as input to the physical design. Logic design is also done. So, you do some kind of block level placement. So, you are doing some, as output you are generating block level or higher level global placement. So, what are the things you are doing? Well, chip planning means you have already done IO placement, you have already done power planning. Now, you are doing performance driven trial synthesis and floor planning. This is a new step which you include in the performance driven design flow. So, what does this involve? This consists of block shaping, sizing and placement, and as we had seen earlier, we can assign some weights to the net weights depending on their criticality, slack values. Then you can just analyze the global net roots, and for the ones where slack values are negative, you can use some buffering, and here at this level you can do some approximate timing estimation using some timing analysis. So, if it passes, you move on to the next step. If it fails, you again go back and again you modify your placement. So, I had said, as I had said, that this is not a single process, it is a continuous iterative process. Several iterations are carried out. Okay? This is the first step. Then from block level global placement, you move to physical synthesis. So, what do? You start with a global placement with, of course, net weights, optional net weights. Then you do some delay estimations, you can use buffers in this case. Then you carry out static timing analysis again. If it fails, you again go back and change the placement. Okay. Now, this delay estimation using buffers. So, here the details are shown here. So, what you do? You do some physical or virtual buffering. Physical buffering means you introduce some buffers, or virtual buffering means you indicate that here you may require a buffer, but you do not introduce right away, you may need to introduce it later. So, for physical buffering means you are actually introducing the circuits, the buffer, the inverters. So, here you have to use an obstacle avoiding global network topology, because you are inserting the buffers, you have to connect them to the input and output lines, you have to see where the circuits and obstacles are already there, you have to lay the nets like that. So, layer assignment, buffer insertion, these are the important steps here. Okay. So, next comes, after physical synthesis done, the routing. So, here timing correction is one step, where wherever there is a negative slack, you make some corrective actions, like using the methods I have already mentioned just some time back, and again you use static timing analysis. If there are some violations, you repeat this process. So, here timing correction can involve timing driven restructuring, gate sizing, and restructuring can be using Boolean restructuring, pin swapping, redesigning fan in trees, fan out trees, all the techniques that we have just now seen, okay, in the last lectures. So, you do all these things so that this timing constraints, whatever was there, was met. Physical synthesis is done. So, now this is the last step. So, you finalize the locations of the sequential elements. Now, you synthesize the clock network once they are finalized. So, after the clock network has been synthesized, you do this once more, global routing, layer assignment. Again you check the timing, timing driven, congestion driven, detail placement, like you check for the timing here, static timing analysis. If it fails, again you go back, again you modify it. But if the timing analysis passed, then you proceed to timing driven routing. So, during this routing you may have to again insert buffers, you may have to carry out some timing correction mechanisms here. So, once everything is done, then you do detailed routing, then you can do some parasitic extraction, some additional steps of simulation, and finally you proceed to sign off. Sign off, what you do here? You check for, as I said, manufacturability, electrical properties, reliability, verification. So, everything passes, then only you proceed to generate the masks for fabrication. But if it fails, then you go for a step called eco placement and route. Eco stands for engineering change order. So, what it refers is that this refers to last minute changes. That means, you are in a step which is just one step before the final fabrication. So, at this step you find that, well, with respect to manufacture reliability there is some problem, let me make some small corrections. You go back, make these small corrections, run timing analysis again. If it passes, okay. If it fails, again make some small changes. Okay. So, in this step, what are the things that are done? Design rule checking, one thing I have just mentioned, layout versus schematic. So, you had a layout initially, you had the schematic diagram, you can make a comparison that whether they are matching. There are some electrical effects like antenna effects, electrical rule checking. You may also have to do all these things at this step, and there are some well defined templates using which these checks can be carried out. Because one thing understand, ultimately your layout is a huge thing, there are millions and millions of rectangles, you will have to do this check over this entire rectangle. Unless it is a feasible and simple process, you really cannot do it. Okay. So, this is the thing. So, I think with this we just come to the end of this lecture. In the next lecture we shall be seeing some additional timing correction methods, and we shall be having a relook at the insertion of buffers and drivers, design of drivers, buffers, etc. So that you can just use that information to just correlate with whatever we have said just now. Okay. Thank you.